Okay, let's start. So in modular arithmetic, we started solving linear equations of a very simple type, Ax congruent to B mod n, where ABN is given. So this basically entails computing inverses, reciprocals mod n, that we have analyzed. It exists only when A and n are co-prime. And then we saw that because of this condition, for prime numbers, inverse always exists, except in the case of 0. Right, so we took a diversion to this Fermat's little theorem, e to the p minus 1 is 1 mod p. Any questions till now? So the next issue is basically we have shown that a raised to p is a mod p. Right, so what can you say for a raised to n mod n? So in case n is prime, we have shown that a raised to n is a mod n, but if n is composite, moreover a is, let's say, co-prime to n, in that case what is a to the n? Sorry, is it? Yeah, so then Fermat's little theorem kind of result is not there. Can you think of an example? So for example, if you take n to be 4 and a to be 3, so what is 3 to the 4 mod 4? This is 1, right? So this is not 3. So hence for composite n's, even if you choose good a's, for example here there is no problem, a inverse exists, a is a number co-prime to n, still a to the n can be anything. Right, so this means that this Fermat's little theorem is not a coincidence, it's a very special property of prime numbers, it's not visible otherwise. And of course, if you take a bad a, then even worse things can happen. For example, if you take a to be 2, what is 2 to the 4 mod 4? Yeah, so if you take a bad a which is actually sharing a factor with n, then it can even be 0. So very far from being a, right? So anything is possible here. So you can actually use this test in a way to get some confidence whether n is prime number or not. It can be thought of as a primality test, which raises the question, how will you compute a to the n mod n? So again, n we consider in computer science very large, right? So n can be thousands of digits, which means that n is something like 2 raised to 1000 or 10 raised to 1000. And even if you take a very small a like 2 raised to 10 raised to 1000 is impossible to compute exactly, right? So how will you do this computation? You cannot just do a for loop, you cannot just keep multiplying n times, because that will again take infinite time. So any ideas? Sorry? Couldn't hear. What? Yeah, so something we did in a numerical example. You use that. So here you saw that 39 was a big number. I mean, you will hate to do this manually 39 times, right? So we did this systematically. We wrote it in powers of 2, basically in base 2. And then when you do in base 2, you have only few numbers. And you can start from the smaller one, which is 2 raised to 1. Then you square it, you get 2 square. Then you square it, you get 2 raised to 4. And you square few more times, you get 2 raised to 32. So you have to multiply only 4 things after few squarings and few multiplications. And every time you do the modern arithmetic. So that is the trick which actually you turn into a fast algorithm. So this can be computed very fast. So this is easy to compute by repeated squaring. So assuming that modern arithmetic is fast, which will be very fast, because in terms of the digits of n, you can always do division and find the remainder. Everything can be stored in that much space. There is no space blow up, there is no time blow up. And on top of this subroutine, so if you have written a subroutine for modern arithmetic, then using those subroutines, you can just square numbers, square remainders and multiply remainders. In few steps, you will get e raised to n mod n value. Okay, so this is a very fast algorithm to implement. So you can, I mean, when n is prime, you will know that a to the n is a, so then there is nothing to compute. But if n is composite, then what the value is, this can be done practically for very, very large n also. So any questions? Okay, so let us finish the linear equation part. We did not get to the final conclusion. What is the solution for Ax congruent to B mod n? Where you want to compute, where you want to find x. So here, what are the steps now in this algorithm? What will you do? So first you will check whether A inverse exists, right? Which boils down to what? Checking what? Doing Euclid GCD. So you compute A comma n. Call it G by the Euclid algorithm. So if everything is fine, which means G is equal to 1, then you can just stop. Then X is just B A inverse. Right? Euclid GCD will also give you A inverse. You multiply with B, that you output that number. And what do you do when you are in the bad case? If G is greater than 1. So this is the case of G greater than or equal to 2. So in this case, actually, more tricks are needed, but you have seen those tricks. What you do is divide that given equation throughout by G. So you will get what? Let's write this equation in new form. So it's A by G times X, B by G mod N by G. Right, this is the equation which is given to you. With slight modification, we found the GCD and then we divided A by G and N by G, which is allowed. Can you divide B by G? Yeah, I mean, B can be, for example, 1, right? Then you cannot divide 1 by 2. So when you cannot divide, what happens? Exactly. So if this doesn't exist, if G does not divide B, then your output fail. Okay, so then somebody tricked you, you were given an equation which has no solution. How do you prove that there is no solution in this case? Yeah, I mean, you just look at the definition of congruence. So Ax is equal to B plus Kn, right? So G divides N, G divides A, so G is forced to divide B. If G doesn't divide B, then it means that it's a failure case. There is no solution. So that's the easy case. So there you don't have to do anything. So now you have a new equation, which is A prime X, B prime mod N prime. Right, so here A prime, B prime, N prime are integers that we have computed, and you have to find an X. So just to avoid confusion, let me call this also X prime. Okay, so you will find a solution in this smaller equation X prime, and then now you have to output something for X coming from X prime, right? So first, what do you know about A prime, N prime here? Exactly, so you know that A prime, N prime they are co-prime. So since you know that, you will output, well, or you will, yeah, you now know that, okay, just maybe it's a computation step. So you compute X prime to be B prime by A prime. Okay, so that is easy to compute, like step 2. Sorry? Yeah, sure. No, reciprocal and inverse is the same thing. When it exists, it exists. You can use any of the notation. If it doesn't exist, then you are not allowed to use this. But the question is, what do you output? Can you output X prime? Is X prime an honest answer of your program? No, what if you outputted just X prime? What does it mean? Exactly, so you observe or you prove that actually X prime is a valid solution. You can show that Ax prime is B mod N. Okay, so if you calculated Ax prime mod N, you will actually get B. So X prime is a valid solution. So you could output X prime at this point and hold and stop the program. But the claim is that there are more solutions than x prime. What are the other solutions? Exactly, so you should actually output that. So you output x prime plus k times no, I don't think it's kg, it should be k and prime. For k, let's say you can take 0, which is just x prime, but you can also go higher, you can go up to g. Okay, so this is the solution set. Is this clear? You can easily check that if you take any of these numbers, so let's say g was 2, right? So there are two numbers, x prime and x prime plus n prime. Any of these numbers, if you multiply by a, then you should get b mod n. Is that clear? If you don't see that, then you should definitely do this as an exercise. Then you will see that it's obvious. So, so with that, your program will actually find all the solutions. It will say that there is no solution, or it will say there is unique solution, or it will say that, well, there are multiple solutions and these are the only ones. Okay, this is a complete computer program to solve linear systems mod n. Any questions? It just uses Euclid GCD. And it's obviously very fast. So even if n is thousands of digits, this will work within milliseconds or seconds. On the other hand, if you didn't use this program, then the brute force method would be that you try out all values of x, which is 0 to n minus 1. Right? So for thousand digits, the 0 to n minus 1 is a very big set. So clearly this is exponentially better than brute force. Any questions? Okay, if no questions, then you can work this proof out for the program and think about what happens if you have more variables, like a1 x1 plus a2 x2 equal to b mod n. Right? What will we do in those cases? That also is not very hard. So, okay, so assuming that we have solved linear systems, let's move to more complicated things. So first what we will do is we'll try to correct this problem that a raised to n is not, a raised to n mod n is arbitrary. Okay, we don't like this result. So we'll try to change this expression so that it gives us Fermat's little theorem back. Okay, do you know how to correct this? You know a lot. So okay, we'll do phi, which is called Euler's torsion function. Okay, so this is something very simple. What you want to study is numbers co-prime to n. In Z/n. Okay, so for, I mean, especially this will be interesting for composite numbers. So if you have these numbers 0 to n minus 1, which ones are co-prime to n? So the definition of that is it's a subset. It's z slash n star. Okay, so this is the elements A in Zn such that A and n are co-prime. Okay, so this is the set of co-prime numbers, and its size is phi n. Okay, is this clear? So in these integers 0 to n minus 1, which are basically all our integers, once we fix n, we are looking at just these n integers. Which of these are co-prime to n? That number is called phi of n. That count is phi of n. It's called the Euler's totient function. So what is phi of 2? In fact, what is phi of 1? So phi of 1 is not very clear from the definition. Let us just define it as 1. Well, okay, from the definition also it's fine. Z slash 1 has, it has only 0. And there is some anomaly there. So we say that phi of 1 is by definition 1. But what is phi of 2? This follows from the definition. So phi of 2 is 1, right? Because you look at 0 and 1, the only thing co-prime to 2 is 1. So there is only one element, and so on. So phi of 1 and phi of 2, they are equal. What is phi of 3? Yeah, phi of 3 is 2. What is phi of 4? Phi of 4 is also 2 because there is only 1 and 3. And what is phi of 6? Yes, phi of 6 is much bigger than 3, but still the number of numbers co-prime to 6 is only 2. Namely, just 1 and 5. And finally, what is phi of 5? This is 4, right? So this is enough experience for you. With this experience, you can immediately prove that phi of n is n minus 1 in what case? Yeah, only when n is prime. And we always assume greater than 1. So for n equal to 2, this is correct, and n equal to 3 and so on. Right, because it has to be correct, because if n is prime, then everything is co-prime except 0. So there are n minus 1 elements. And for n greater than 2, phi n is at least. Yeah, what is the proof of this? Yes, so the certificate is 1 and minus 1, right? 1 and minus 1, so minus 1 is basically n minus 1. Those two elements will always be co-prime to n. So hence there are always at least 2 co-prime elements, so phi n is at least 2. But as you can see, phi n is neither increasing nor decreasing, right? It fluctuates, it depends on n in a complicated way, and we'll completely analyze that. We'll give a closed form expression for phi n in this class. And right, so since it fluctuates, you can see that phi of n equal to phi n prime doesn't mean anything. It doesn't imply that n is n prime, right? So for two different, for the number n prime which is much bigger, still the phi can be equal, right? Like we saw for 3 and 6, 3, 4, 6. Okay, so something slightly more challenging is for a prime p, what is phi of p square? How do you analyze this? Right, so you do this by complement. So it's p square minus the numbers such that they share a factor. The number of this. Right, this is the opposite of the definition of phi p square. So phi of n is n minus this. In our case, n is a square of a prime number. What is now that count? How many a's are there which share a factor with p square? So you show that they have to be multiple of p. And how many multiples of p are there? That's p, right? So phi of p square is p square minus p, which is what we saw for phi of 4, right? So that's 4 minus 2. And from this, what do you learn about prime powers? So phi of p to the k is what? So if you did the same thing for p cube, you will get p cube minus p square, right? So in general, you will get p raised to k minus p raised to k minus 1. Or you can also say p raised to k times 1 minus 1 by p. Right, so this is the expression for all k greater than or equal to 1 and p prime. Is this clear? So we are making great progress because now we understand this function in the case of prime and also their powers. Right? So all that is left is product of prime powers, because every number n can be written as a product of prime powers. So can you connect now, let's say phi of p and phi of q with phi of pq? What do you think it should be? So in case you have two different prime numbers, when your n is like this, p times q, how is phi of n related to its factors? That is phi of p and phi of q. Any guesses? Sorry? Yeah, so when you are asked to guess, you should make the simplest guess, which is that it should be product, right? So phi of PQ should be equal to phi of P times phi of Q. Clearly it is not true when P and Q are equal, because phi of P square is not phi of P times phi of P. It is something larger actually, but that is fine because phi of P square we have understood. What we don't understand is when P and Q are different. In that case something good will happen, which is this product. So let's prove that. So this is the multiplicative property. So what we'll show is that if m comma n are co-prime numbers, then phi of mn is phi of m times phi of n. Okay, so we'll show that the Euler-Totient function phi is multiplicative, but it's not totally multiplicative. It is multiplicative for co-prime numbers. Okay, but in the number theory, this also is fine. So when we say an arithmetic function is multiplicative, we always mean this. Otherwise, we will say totally multiplicative, which in this case is false. So how do you show such a thing? How will you show that this identity holds? Sorry? Same thing. Can't be the same thing. This looks more complicated. So there we just use complement set and it turned out to be simple. Here if you try to do that, in fact, yeah, I leave it as an exercise. You use inclusion, exclusion and the same thing. Yeah, so that can be done. But there is a more beautiful proof which we will see here. So what we will do is we will study 3 sets. I mean, they are by the definition of phi. So the 3 relevant sets that we want to understand are these, right? The Z, Zm star, Zn star and Zmn star. Right? These are the 3 sets, and what we want to show is that the third one size is the product of the 2 other sizes. Like the cardinality factors, cardinality multiplies in this way. So instead of just talking about the cardinality, we will actually make a statement about the set itself, which is that we will show a bijection from here to there, which we can denote as psi. Okay, so if we can show a bijection, then it means that well, the cardinalities are the same, and the cardinality of a Cartesian product is product of the cardinalities. So we'll have the result, right? So we'll show something far stronger than what the theorem is saying. We will actually show that these 3 sets are under a bijection with using the Cartesian product. Is this clear? Okay, so once I tell you that there is a bijection map psi, can you guess it? What should psi map? So what do you have to find? You have to Yeah, so A is an element here and B is an element there. So this tuple, this pair A comma B, you want to map it to single element. So this element, let's call it C. Right, so every pair you want to map to a number C. That will be the definition of psi. So what should you do with AB? How should you construct C? Given two integers, what do you think is the third integer? You can multiply AB, you can add AB, and then what the answer will be C, right? Those are the only options. So what should you do? Sorry? Yeah, product or just sum or just product are bad options because see, the problem with product is that the arithmetic in the image is mod mn. So if you by chance took B to be A inverse, then A inverse will become 1. So many elements, actually many pairs will map to 1. So clearly that is not a bijection. So you have to do both. You have to multiply these with something and then you have to add so that it's complicated enough so that there is nothing bad happening. So what is that complicated linear combination? Sorry? 10 into A. N into A, okay, yeah. Yeah, so that should be clever enough. So what you do is you multiply A with N, B with M, and then add. So it remains a linear combination of A and B. So let's try that. And obviously reduce mod mn because there is nothing more in the image. Arithmetic is mod mn, so multiply n, A with n, B with m, add, and then reduce mod mn by division and remainder. Okay, so that's a simple expression. All that remains is to show that this is a bijection, right? So let's do it in multiple steps. So the first property you want to show is that it's a valid map. Whenever you construct a map, potential map, you should check whether it's actually a map. So what does it mean? What do you have to check? To check for validity? Sorry? So here the issue is that this A is a residue class, right? A and B are residue classes. So you have to check that instead of A, if you took A plus Km, and instead of B, if you replaced it by B plus Kn, still the answer which you will get C, it will be the same. It will be the same residue class. Okay, that's the thing with validity here, because if you remember the definition of Z mod Z slash M, it was via residue classes. And the residue class has infinitely many things. So A is not actually one number, but it's infinitely many numbers. So to show validity, to verify validity, what you have to verify is that it doesn't matter what A you take and what B you take, answer is always the same. Do you see that happening? Because if you perturb A by a multiple of M, then outside there is an N, right? So N will multiply with M. So mod Mn, the value will not change. and the same thing with B. Okay, so actually, if you think about validity, then this definition is the only definition. So this is a canonical map to come up with. So, oh, and another thing is that in validity, you also have to check that what I am saying, NA plus MB, it's actually in the image, which is that it should be co-prime to Mn. Right, that's also an important thing, because it's very easy to fool me, it's very easy to fool myself and you in giving a map which actually doesn't even lie inside the range. So that also is true here. Let's write those properties down. So basically, NA plus MB, first of all, it mod Mn doesn't change as long as we pick residue class A and B. So its value, which is a residue class, will not change. That is because we have multiplied A with N, and A itself is mod M. And second important thing is that NA plus MB mod M is in this set, because maybe we have to do this by contradiction. We have to properly prove this. So suppose NA plus MB with Mn, they share a factor G, and that the GCD is G. Let me just do the symmetric case, one case which will suffice. Suppose that NA plus MB shares some factor with M, right? I mean, if it shares a factor with Mn, then it has to share a factor with either M or N. So let's just take a simple case that it shares a factor with M. What do you deduce from this? Exactly, you can drop MB. So this means that NAM is also G, which means what? See, so M and N we have assumed to be co-prime, right? And G divides M. If G divides M, then G cannot divide N. I mean, G will be co-prime to N, so it's something stronger. But it has to divide NA, which means that it divides exactly A. So A comma M is then G. Which means what? No, contradiction to what? Yeah, so recall the domain of A. A was in Z/M star, right? So it was co-prime to M. If it was co-prime, then G has to be 1. That's the thing. So you can do the symmetric case with N also, and then you can club and get Mn. So ultimately, Na plus Mb is co-prime to Mn. Is that clear? So hence, the definition works. I mean, the definition is valid. We don't know whether it worked, but at least we have checked that it's a valid definition. It is taking a pair of residue classes, and it is giving a residue class which is co-prime to Mn, right? So we have checked that the domain is domain and the range is range, right? That's the first important thing to check. So second thing you have to show is that psi is injective. So what do you have to do to check that? So injective means that two pairs should not map to the same thing, right? So suppose they do. Suppose Na plus Mb is Na prime plus Mb prime mod Mn. Right, so you took a pair A comma B, another pair A prime B prime, and their images are the same. So then this congruence is satisfied. What do you deduce from this? No, not too fast. So let's bring n together. So if you arrange in this suggestive way, so you have n times difference same as m times difference mod mn, right? So from this you can again use that coprimality trick or the cancellation trick, which is left hand side has to be divisible by m, but m and n are co-prime, so then a minus a prime has to be divisible by m. Or you can just write simply like this, right? So m has to divide, or maybe let's do that step. So this means that m divides n a minus a prime, which means that m divides a minus a prime, which means what? Yeah, which means that a and a prime are the same residue class, and similarly b and b prime are the same residue class. So symmetrically, and then combining them, you learn that actually a comma b and a prime b prime were the same to begin with. Okay, they are the same element in the Cartesian product. So which means that this map is injective. Okay, different elements are mapped to, or different pairs are mapped to different elements, different integers. So that is what was the problem if you just took product of A and B, because a lot of things were mapping to the same, so it was not injective. So this is an injective map, and the last thing to check is that psi is surjective. Which means what? Yeah, which means that if I take a C of my choice, there should be an AB. There should be a pair AB. So pick C in this range. So what you have to find is A comma B such that psi of A comma B is C. So basically you have to consider this equation NA plus MB congruent to C mod Mn, right? So this is the, what is unknown here? A and B are the unknowns. So this is the exercise I had left. Linear system or linear equation even, there is just one equation, but there are two unknowns, A and B, or think of it as X and Y in the previous setting. So how do you plan to solve this? How do you find A and B? Mod M. Yeah, so if you go mod M, then what do you learn? So mod M will tell you that NA is C mod M. Yeah, so again you use the fact that N and M are co-prime, so N inverse exists, so A is, it's actually if and only if, there is no loss of information, so A is C by N mod M. But remember that this A that you are getting, it's only mod M, while in the red equation you want everything in mod Mn. Yeah, so here you observe that actually A is a residue class mod M, so by this calculation of mod M, the only possibility for A is C by N. Okay, there is no other possibility. But you have to show that this possibility works, which means that you have to find a B that goes with this. What is that? So you do this symmetrically. And this will give you that B is then C by M mod N. And now you verify that N times this answer that you have C by N mod M, yeah, that will be error inducing. Let's not write like this. Let's also not do this. Basically, now since we have found A, let us just plug it in and find B. Okay, don't find B independently. That will not help. You have found A, so B is now kind of unique. So you plug this in, so what do you get? NA, MB is C minus NA, which is the one that you found above. Okay, you have found some number A, which is C by N, C multiplied by the N inverse mod M. That number you plug in here, and C minus NA then has to be MB because you want the solution to that red equation. And from this, what should B be? So B has to be C minus NA times M inverse. Well, that's a problem. So what should we do? Yeah, so you have to think about this equation. We cannot divide by M because we are doing arithmetic mod Mn, right? So M is not invertible. What should you do? Yeah, so you observe that in the previous line, what you had is that C minus NA is divisible by M. It's a number which is divisible by M. So you can actually not compute the inverse by Euclid GCD, but you write it like this. You just do integer division. Okay. So C minus Na is a number divisible by m, so you divide and then you get another integer, and that integer mod m is your b. You use that b. Implies that b is found, and this implied that a is found. Okay, so we have found A up to mod m residue class, and we have found B up to mod n residue class as required. Is this clear? Any questions? Just one thing you have to check, whether they are really in the domain required, which is z slash m star. Is A there? Is A co-prime to M? The A that we have found here, is it co-prime to M? Anybody else? One person seems to know all the answers, but others are confused. So A is C by n mod m. C you started with as a number which was co-prime to Mn, right? So A will also be co-prime to M. Sorry? We can find what? Yeah, no, but we don't need to find A inverse. No, you just observe that since A is C by n, by definition of C, it's co-prime. It's co-prime to M. So you just check that. I mean, just fill in that detail that A is indeed in Z M star and B is indeed, so B is in so the way we have defined A and respectively B, it's automatically co-prime to M respectively N. That is all we needed to do. Right? For any C we pick, there is actually a fast algorithm to find AB. Right? Everything here is explicit, which shows that psi is surjective also. So psi is a valid map which is both injective surjective, so it's a bijection. So since psi is a bijection at the level of sets, of course the totient function is multiplicative. Okay, any questions? Okay, so this proof uses a lot of things that you have learnt in this course, and it proves this interesting property that now the totient function you can write down completely in a closed form. Let me just write that down, it follows directly. So suppose n factors as this. Is the prime factorization. Then what do you learn about phi n? It's multiplicative, right? So phi will go inside. Because this factorization means that pi's are distinct primes, right? So they are co-prime. So pi to the ei are also co-prime for different i's. So you can repeat the previous property repeatedly, and you can bring phi inside. So phi of n is actually product of phi of the prime factors or prime power which appear in the factorization. And what do you know about pi ei? That we have computed previously. So it's pi ei times 1 minus 1 over pi, which is n times product of 1 minus 1 over pi. Right, so we have this nice closed form that phi n over n is product of 1 minus 1 over primes that divide n. Right, so we can also write it like phi of n by n is product of p that divide n 1 minus 1 over p. Okay, so you can compute phi of n as long as you can factor n, which will be a very difficult problem if n was very, very large, like 1000 digits, you cannot factorize n. Currently, there are no fast algorithms known, but at least mathematically, you can say this is a closed form expression, right? Nothing is missing here. You get phi of phi n over n exactly, as long as you know what are the primes dividing it. You actually don't even need complete factorization, you just need the primes that divide, or you just need this product of 1 minus 1 over p. Okay.